Okay, here is our next video on standard model of particle physics. So the standard model of particle physics is now where we get to look at everything that's been happening. Okay, this what I have on the screen. It's not the most updated model, but I do like that it shows a lot of information that's on the screen here. So the standard model of particle physics, what we're really looking at, what composes everything in the universe. Um, I mean, not dark matter, but we just won't even touch on that. But everything of the observable universe, everything that we know, is made of these things on the screen, plus a couple of others that are missing but aren't important for our purposes. Okay, in kind of our top left corner up here, in the top left corner, I don't have purple, so blue will have to do. Top left corner, we have these things called quarks. Quarks are what make up like protons and neutrons, everything that is kind of this bigger particle that we have. These quarks are what makes those up. So a proton is composed of a packet of an up quark, and a down quark. A neutron is composed of a packet of an up quark and two down quarks. You do not have to know this. I should have started the video off by saying this. You do not have to know this. Well, you don't have to memorize this model, I should say. IB physics does have to memorize most of this information here, but the AP Physics 2 test does not make you memorize this. At least at the time of recording this video. So the protons here, right, you can see, right, protons have a charge of +1. You can see if we take an up quark, and a down quark, right, an up quark, and this is why I like this chart. This is why I picked this chart, even though it's not the most updated. But an up quark, you can see, has a charge of 2/3. So a charge of 2/3. That's for both of the up quarks. And the down quark has a charge of -1/3. So what happens if you take all of those charges and you add them up together? 2/3 plus 2/3 minus 1/3. That gives us a charge of 3/3 or +1. Okay, how about a neutron? All right, those up quarks have a 2/3, the down quarks have the -1/3. So if you add those all up together, we get a charge for a neutron of 0. That's where the charges come from. It's just the quarks that make them up. As far as why these quarks have these specific charges, that is, well, if you can answer that question, there might be a Nobel Prize in that for you. Okay. So we've got the charge, we've got the, we won't worry about the spin. Don't worry about the spin, or the mass, really. We'll get to the mass being important at later times. But for these protons and for these neutrons, right, up, up, down, and then up, down, down, it makes a proton and neutron. All that to say, you don't have to remember that a proton is an up quark, and a down quark. You do not have to remember that, or vice versa for a neutron. What you do have to remember, the things you do have to remember are that small particles make up big particles. I know that sounds kind of intuitive, but there are actually questions that AP will ask about like a small particle decaying. Like maybe they'll take one of these leptons. Meant to grab the green marker here. So we can take these leptons. That's an entirely different category. All right, so we've got quarks, we've got leptons. And these leptons are things with a mass of essentially 0 for the most part. They're just so small compared to some of the other things that we will oftentimes consider them with a mass of 0. However, you can see that that kind of goes away when you look at like this tau particle over there. It just, general classifications, you don't have to know why they're in these that they're in these sets as they are. But basically, a lepton is its own thing. These leptons, you can have the opposite of these leptons. Actually, you can have the opposite of every single one of these particles. So we have an up quark. You could also have this thing called an anti-up quark. You could also have like an anti-down quark, charm quark, strange quark, top quark, and bottom quark. Whoever named these just had a field day, but they were having a lot of fun. Probably were too busy out having a good time after they won their Nobel Prize for all of this stuff. But this standard model of particle physics, right? This lists just all of the initial particles, but every single one of these in the quarks and in the leptons area has its own anti-particle. So, right, an electron is electron with a charge of -1. Its antiparticle is a positron, an electron with a charge of +1. Right? You can have a muon, and that's got a -1, right? Its antiparticle would be a positive muon. And there's fancy names for all of these, and you can have as much fun as you want looking up all the names to all these different things. But same thing with the tau particle, right? Tau, you can see, has a charge of -1. Antiparticle would be tau with a charge of +1, all that kind of good stuff. Underneath those, you see that these leptons are kind of paired with neutrinos, right? We've got an electron neutrino, a muon neutrino, and a tau neutrino. What these neutrinos do, essentially, is we've observed that anytime an electron gets created, right, and this could be a creation from a different particle breaking apart into its component parts, or something we'll look at is energy can just turn into one of these particles, which is kind of cool. But anytime we create one of these particles, we also create its neutrino. So if we were to take, and I know the last video looked at this, if we were to take a gamma ray photon, they have a lot of energy, right? Gamma waves have high energy. But excuse me, this gamma photon, if we just created a random electron and its antiparticle, a positron, what that also kind of does is we created an electron, we have to create an electron neutrino. And then we created this positron, which means we have to create an anti-electron neutrino because this positron is an anti-electron. So because we created an electron, we create an electron neutrino. Because we create a positron, we create a positron neutrino, or an anti-electron neutrino. You don't have to know all this to have it memorized. All of this is just to give you an exposure of what does everything mean on this sheet. What does everything mean on the sheet? Because there's a lot. There's a lot that's on here. There's a lot that you could get into. You could go pretty deep down the rabbit hole if you're just having fun on the internet, looking up standard model of physics. But what this is going to lead you to, honestly, is more questions than answers, because this is where physics just stops. This kind of stuff right here, we don't know anymore. So anything that's further information off all of this, that will earn you a Nobel Prize. To be perfectly frank with that. One thing a story that I really like is there was on one of my college campus tours, there was someone very obviously not a physics major who was giving a tour for people who are prospective to be involved in the physics department. And here they were saying, oh yeah, physics, it's kind of old news. There's nothing new to be discovered in physics. And while that's pretty much true of classical physics and mechanics and, right, the motion of objects, that's pretty much true. However, it's not true just as a whole, because there's so much in this one little sheet right here. There's so much to unpack right there, and a lot of it we just don't know. We really just don't know, and it's spectacular, I think, that there's things we don't know. So I love being able to leave you toward the end of the year, leave you with this wonder of physics, and we just don't know this stuff. Um, anyway, besides my awe of everything that we don't know, just getting down to this, I mentioned this before. AP does expect you to know that small particles make big particles. Small makes big, as far as these particles are concerned. What that means, let's say we get I'll slide down here. Let's say we get a muon. Right, this muon, they have a negative charge, if you can see from up here, right? Muons, charge, -1. If we get a muon that decays, let's just say, what might it decay into? How would a muon decay? What would it split apart? Maybe it goes into three things. Who knows? Let's just give a couple of possible options. Could a muon, right? Okay, it's got a negative charge. I'll give you a couple options. Let's say you got option A. Let's say a muon decays into, let's see, a proton plus a electron. Let's try that out. Or let's say it decays into a neutron plus an electron. Or let's say maybe it decays into, right, a neutron and why not a tau particle? I'm just giving random answers here. Let's say another option, maybe it decays into an electron and, a pair of neutrinos. Okay, let's just get a couple of options here. Let's see which one of these, which ones of these are possible. Well, basically, how this is arranged: quarks are small, leptons are a little bit bigger, but then these things that quarks make up, like protons and neutrons, those are called hadrons. You do not have to know that. But those are both classified as a thing called a hadron. That's actually the CERN super collider. In CERN, Switzerland, is called the LHC, or the Large Hadron Collider. That's what they mean by it. Hadron is basically just protons and neutrons. But protons and neutrons doesn't sound as cool when you put it in an acronym. So those are the largest particles that you can get, really, at least as far as we'll look at, are protons and neutrons. So if we start with a proton and a neutron and we break it down, we could get a lot of these other things. However, if we start with something that's smaller and break it down, would it just randomly turn into a proton or a neutron? Well, no. So write this practice problem down here where we have a muon decaying. I'm sorry. I really should give you one more option here. Let's say a tau particle plus, that zoomed out way too much. A tau particle plus a neutrino, just one neutrino. Okay. So if we have this muon decaying here, pair of neutrinos. A muon decaying, well, muon is one of these smaller particles. So can a muon ever decay and then we get a bigger particle out of it? Well, no. So that means we can't get a proton. That means we can't get a neutron out of this. Right? No matter how much we want to look at this, right? A proton plus an electron, that would give us a charge of 0, which actually wouldn't match up with our charge of -1. So that one we could eliminate by charge, or by saying a muon will not decay into a proton because a proton's bigger. Another thing is, right, neutron plus electron. This would give us a negative charge. That's okay charge-wise, but it can't decay into a bigger particle like a neutron. Same thing with a neutron, right? 0, tau particle, -1. And you don't have to remember these charges, but if you see neutron, you should immediately say, oh, no. Okay, can't do that. Okay, all we're left with now is an electron and a pair of neutrinos, or does it go into a tau particle and a single neutrino? Basically, two ways to do this, and this goes beyond, but it's something that I can at least bring up, but it goes beyond the AP Physics 2 curriculum. A neutrino gets created when you either create or destroy a particle. So when you create a tau particle, you will get a tau neutrino. So a tau particle, you would get a tau neutrino. But when we destroy this muon we're looking at for the whole problem, that means we have to create, this would be creating an anti-muon neutrino. So we would really, we'd be getting, we'd be getting we'd be getting two neutrinos, right? One to go with the tau particle and one to go with the muon. So we can't just be one neutrino. It has to be two neutrinos. The other thing we can look at would be over here. All right, a muon, you can see its mass up here, 105 mega electron volts per c squared. It's weird, but this is it's a unit of mass when we're talking about particles, and we'll get there. We'll get more practice with it. But then a tau particle is 1.77 giga electron volts per c squared. Right? Giga means times 10 to the 9. Mega means times 10 to the 6. So this is almost 1,000 times bigger than a muon. So since a tau particle is bigger than a muon by almost 1,000 times, it can't be a tau particle that it turns into. So we definitely just have this one left. We've got an electron plus a pair of neutrinos, right? Because we create an electron, so we get one neutrino. We destroy a muon, so we get a second neutrino, so we get that pair. You don't have to know that all. This goes way beyond, just to give you an introduction, everything you can do with particle physics and the Standard Model. Here's what AP wants you to remember in one little bubble. Small makes up big. So small particles will always be the ones to make up the big particles. You cannot have a muon decaying into a proton. It just doesn't work that way. An electron will never decay into a neutron. However, it can go the opposite way. So that's one thing they want you to remember. A second thing they want you to remember is conservation of charge. Right? Whatever charge you start with, you have to end with that amount of charge. Period. End of story. No exceptions to that one. Conservation of charge, one of our fundamental laws of physics, just like conservation of energy, conservation of momentum. So there's our conservation of charge. That's what AP really wants you to remember. Small makes big, conservation of charge. If you remember those two things, you'll be just fine. I expose you to a lot more in this video than you have to know, just because it gives you an access point, right? You can start to look at these things in terms of the Standard Model and of what you know. But you don't have to know it all. Just remember these two things down here. You'll be just fine for the AP test. If you have any questions, let me know. Otherwise, that will conclude this video.